Good day, learners. Welcome to our today's mathematics lesson. My name is Snagile Ndlovu. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Okay, boys and girls, welcome to our session. Like I've already indicated, we are focusing on trigonometry functions. My name is Snagile Ndlovu. Right, by the end of this lesson, you should be able to sketch a graph of any of the trig functions defined by y is equal to sine theta, y is equals to cos theta, and y is equals to tan theta for any given domain, but in particular, we are going to sketch these graphs in the given domain. X is an element of the closed interval negative 360 degrees to 360 degrees positive by using what we call point-to-point plotting of those points. After plotting the points, we'll then join them to produce a particular graph. 2, you should be able to describe the function in terms of its amplitude, period, and frequency. You should also be able, in 3, to recognize or investigate the effect of the parameter k. We shall see what that k is as we deal more with these functions on the graphs of a function or defined functions. Y is equal to sine k theta, y is equal to cos k theta, and y is equal to tan k theta. And by now, I think you are familiar with trigonometry. You were introduced to trigonometry at some point in time in grade 10, and it was defined that trigonometry is that branch of mathematics which deals with the relationship between angles and the lengths of sides of a given triangle. This is where you even drew a right angle triangle, in which case you identified the adjacent side to a particular angle, the opposite side to a particular angle. Otherwise, your longest side in that right angle triangle was your hypotenuse side, which was denoted as r, the vertical distance being denoted as y. Otherwise, the horizontal distance was your x. This is where, again, you established the 3 trig ratios, cosine, sine, and tangent by definition. For example, you defined sine as y over r, and you defined cos theta as x over r. Otherwise, your tan theta was y over x. That was when you were looking at a right angle triangle, trying to define exactly what is sine, what is cosine, and what is tangent on a Cartesian plane. You also did the plotting of points on a Cartesian plane to sketch some graphs between 0 and 360 degrees, just to have a look and see how those points behave on a Cartesian plane if they were to be joined. Of course, you also looked at the general solution to some simple trigonometric equations. Right. You looked at the following terms at that time. We spoke about the domain being a set of all the x values for which the function exists. You also looked at the range of a function, which is the set or collection of all the y values for which the function exists. Then the period of a trigonometric graph is the horizontal distance over which one complete cycle of the graph is completed. You shall see at a later stage that these graphs have what we call a cycle. In other words, they will have to complete a particular pattern before another cycle begins. Hence, they have what we call a period. Then the amplitude of a trigonometric function is half the vertical distance between the highest point, which is the peak of your graph, and the lowest point of that particular graph. We are focusing on the vertical distance. Right, so we are going to focus on 3 functions and try to investigate and see how we draw these particular graphs on a Cartesian plane, and our focused domain is x is an element of negative 360 degrees to 360 degrees. What does that mean? It means we want to investigate the behavior of these functions in a specified region in a selected region, not in the entire domain. Remember, our entire domain runs from negative infinity up to positive infinity. But for today's session, we are going to focus on a specific domain, bearing in mind that domain are those x values for which we are drawing our function. In other words, our domain in this case is going to be a closed domain, meaning we are using square brackets in that interval notation on the x. Right, so we are asked here to sketch the graph of the function f of x is equals to sine of x. Today we are going to be focusing mainly on the functions and their related sketches. If you were to represent these points on a Cartesian plane, what kind of a graph do we produce? That's our focus through plotting some points. 2, you need to determine the following: the domain of the graph f, which is my sine x in this case. You also need to determine the range of the graph f, then the period of graph f, as well as the amplitude of our graph. Right, when we look at the table that has been presented there, I'm going to quickly guide you as to how you can come up with that particular table. Right, I want you to take your calculator, because we are going to have a Cartesian plane wherein we are going to plot some points. We are going to have a Cartesian plane where we are going to plot some points. And I've already defined your domain and have put some intervals there, starting from 0 degrees. I went to 90 degrees. There is a reason why I'm using 90. You shall see as we progress why I used a scale, an interval of 90, as I was spacing out my angles from negative 360 degrees to a positive 360 degrees. I could have chosen any other value to use, a particular value wisely chosen less than 90, but I chose 90 degrees to space up out my angles until I get to 360 degrees. But I did not just choose that 90 degrees. You shall see later on how we choose how to space out angles in a given domain for a particular function. So I want us to complete this table together. There are some steps that I would want you to follow on your calculator. Nowadays, we don't substitute angle after angle, angle after angle. For example, you can take your calculator right now and say, what is the sine? You press sine on your calculator. I guess you all having your calculators. If you are doing maths, must always be in possession of your calculator, especially for such kind of topics. Right, so I want to complete this table. I'm given the domain. The domain is x is an element of negative 360 degrees, and I'm supposed to stop at 360 degrees. So I have negative 360 plus 90, it goes to negative 270, plus 90, it goes to negative 180 degrees, plus 90, it goes to negative 90, and so on until I get to 360. That's how I define values of f of x, which is basically your y. When x is negative 360 degrees, what is the corresponding value for y? So this is where you're going to take your calculator. You press the sine key on your calculator, then open brackets, must always open brackets, and press negative 360, then you close your brackets and say equals. Then you'll get whatever you get there. In this case, I'm getting a 0. So you press sine, open bracket, negative 360 degrees, you close, you say equals, it gives me 0. You do the same for negative 270 degrees, it will give you a 1, up until you get to 360 degrees. You'll end up having what we call an ordered pair, x versus y. That's an ordered pair. But I wouldn't encourage you to substitute these angles in an examination angle after angle, point after point, substituting for 270, substituting for 180, and so on. You can simply use your calculator to so long have a complete table. How do we come up with that table? I'm going to guide you step by step to come up with that table. Right, step number 1. let's discuss it together. Let me quickly insert a page for you. Right, step number 1, you are going to go to your calculator. These are this calculator approach table. We want to have a calculator table for all our functions to save time. Right, the first step is to go to mode. You go to the mode of your calculator, and then you press mode, and then second step, you look for your table. You'll always find table there. Table, then you click on that table. It will ask you to put a function. Right now mine says function, meaning enter a function. Our function is y is equals to sine of x. Our x being English. Right? From there, you enter your function. In this case, mine is sine. Right, for you to enter this variable x, which represents English, that's your variable x representing English, you are going to select x on the calculator. It depends on what color is your x. Some is yellow, so you are going to use second function x or shift x. In my case, it's alpha x. Then I will have the function on the calculator as sine x. Then, so that's our step number 3. You enter the function. Enter the function. The function on your calculator, you enter the function. Right, which is y is equal to sine x. So you just type sine x. You don't have to say y is equal to sine x. The function is just sine x. Then step number 4, as you are using that calculator, you say equals. If your calculator says function 2, it means you can draw 2 graphs at the same time. You can as well feed the second function if you were to compare 2 different functions. Right, but this time around I only have one function, sine x. I'll just say equals. Right, the calculator will ask you, where do you want to start searching for your values? Remember, our domain is x is an element of this closed interval from negative 360 degrees to 360 degrees. That is our given domain by the examiner. So that's what you enter. When they say start, it means your starting point is negative 360 degrees. That's where you start, and that's where you end. It's a closed interval. So what am I going to do now? I'm going to press negative 360 degrees, which is my starting point. Then you say enter. Your enter is your equal sign. You just press your equal sign. It will take you to the next step. The next step says, what is the step? Remember, you have to space out your angles from negative 360 degrees to 360 degrees. So what is your step? How are you going to space out those angles? I already gave you a step of 90 degrees. Step, in this case, is equals to 90 degrees. I will show you later how you get this 90 degrees. So our step is 90. You enter 90 degrees and say equals. Once you have entered the step, some calculators say end. Other calculators don't prompt that end. So you just enter the step, it will give you a table. For those calculators that say end, your end value is going to be 360 degrees. It will say start, you enter negative 360, then press the equal sign. Then next it will say end. So after entering your function, you'll have start for some calculators. Then you put your negative 360 degrees. Then the next step, it will say, where do you want to end to make your table? I want to end at 360 degrees. So after every operation, you press equal sign. That's your enter on your calculator. Then from there, the next step, that is your 6, depending on the calculator, you shall enter the step. This is where you need to consider your step of 90 degrees. Then from there, you are going to get a table. last part is your table, which is going to have your x values this side and your f of x values on the other side. Once you enter, it will so long give you all the numbers in correct order from minus 360, negative 270, going up through 0 and so on through 0 until it goes to 360 degrees being your end point. This is your start point, this is your end point on the table. The corresponding values on the other side are 0, 1, and then it continues with those values until you get to the last value. As you scroll down, you shall get to the last value, which is your 0 for 360. So as you follow those steps prompted by the calculator, you will enter as required. Step number 1, you press mode, then you feed your function without saying y is equal to, you just feed the function is sine x. That x represents those angles. Then when you say enter, it will ask you where do you want to start searching or drawing up your table. I want to start from negative 360 degrees and I want to stop at 360 degrees. You enter on your calculator accordingly. After every operation, you press an equal sign. It will take you to the next step. When they say step, they are basically saying on the calculator, how do you want us to move from negative 360 to positive 360? In how many steps are we going to space out our angles? So we are spacing out our angles in this case using 90 degrees. Then you enter a step of 90 degrees. Having done that, once you say enter, a table will appear on the screen with all angles paired up with an output value, which is a numerical value, which is just but a number. On one side, that is your x values, your angles. On the other side of the table, that becomes your y values. So it means you are now going to have an ordered pair. Right. Let's go back to that table now. I guess you understand now where this table came from. You now have an ordered pair, negative 360. These are your points now. Negative 360 degrees is paired up with a 0, is a point on a Cartesian plane, followed by negative 270 degrees is paired up with your positive 1. You will mark that. Then the next point, and so on. All those are the points until you get to point 0, 0, after which you cross to the positive side, and it will continue until you get to the last point, which is 360 degrees and your 0. These are your ordered pairs now. We took them from the table and we are now forming an ordered pair, which is always in the form x, y. X values being your domain, the input, then your output being the y values. So this is how we come up with a table in these questions. Whether it's sine, cosine, or tangent, you can fit any function. Thereafter, you come up with your ordered pairs, and then from there you design a scale based on the values that I'm seeing here. I can see the minimum value of y is equals to negative 1, and the maximum value of y is a positive 1. So it means I need to design a scale that will run from negative 1 to 1. Okay, then our angles will start from negative 360 degrees to 360 degrees on my Cartesian plane. Right, there we go. We are going to plot our points. This is our Cartesian plane. There is our graph paper. I've already designed the scale for you. It starts from negative 1 going to positive 1. We have marked the points here. Remember, our first point is negative 360 versus 0. You mark that point on your Cartesian plane. Your next point was negative 270, and this is your negative 270, negative 270 degrees versus a positive 1. Then we come to negative 180 and 0. You are plotting those points. You go to negative 90 versus negative 1 down there. you go to 0, 0, then you cross to the positive side of the x-axis. 90 degrees goes with a 1, that is your point up there, and then your 180 degrees, you basically following those values that you are seeing on your calculator. You don't have to necessarily show it in ordered point form. You can just look at your calculator, plot those points accordingly to save time, because these questions normally carry at least 3 marks upon sketching correctly so and joining correctly. Right, then 270 according to my table is -1. And then final 360 degrees is going to be a 0. When you look at all the points that you have marked here, starting from -360 is right on the horizontal axis, is resting, that point is resting, literally resting on the x-axis. That's why we normally say where y is equal to 0. Then it goes up to the next point, which is -270 and 1. Then it comes down and passes at -180, going to the negative values of y. Otherwise, we are noticing a movement of some kind. It's like it's an up and down movement in a smooth curve. So we are going to join those points using a smooth curve until we get to 360 degrees. And then that graph will be defined. So this is the behavior of this sine graph between -360 degrees through 0 to 360 degrees on the other side. Right, so what I'm noticing again here is that as we draw it from -360 degrees at a step of 90 to 360 degrees, this graph seems to be trapped. It seems to be trapped. What do I mean by that? Let's have a look at that. This graph seems to be trapped. It seems to be trapped between negative, if I could draw this line there, -1 and +1. What we see on the board now is called a sine wave. This graph has produced what we call a sine wave. Our graph F, we will label it as graph F. That is its name. Every time you draw a graph, you have to give it a name. Its name is the function itself. It's f of x equals to sine x. So this is just graph F. So what we see here, this graph has produced what we call a sine wave. It's like a wave moving up and down, but it's trapped between -1 and +1. What does that imply? It implies that this graph is oscillating between -1 and 1. The furthest point it can touch going up is a +1. It will never exceed that one. And there is a reason why it can't exceed that one for now. Then as you go down, the furthest it can reach is, or the lowest point going down that it can reach is a -1. Therefore, our sine wave graph is trapped between -1 and +1. This is our line y is equals to -1, where it turns. This is our line y is +1. So we can see this graph only exists going up from -1 to +1. That is our vertical distance. Otherwise, on the horizontal, we can see the graph starts exactly from -360 degrees and stops at 360 degrees. And I guess you are also noticing something on that particular graph. My graph is continuous. There are no breaks in between. There are no broken lines in between. This is what we mean by a continuous graph in terms of movement. So the sine graph in this interval, -360 to 360, is continuous in nature. Then, and secondly, I guess you are observing what I did at the end there is shaded there. Is shaded here. Why is it shaded? Remember, our interval is a closed interval. What do I mean by that? We used a square bracket. X is an element of, we used a square bracket here, meaning both negative 360 degrees and our 360 positive degrees are included. Our graph must start exactly at negative 360 degrees and stop exactly at 360 degrees. Both negative 360 and 360 are included. So far, this is what we are seeing about this graph as we sketch it. It seems trapped and will always be trapped. That is a basic sine graph. When we say it's a basic sine graph, we mean it's a standard sine graph, because these graphs sometimes undergo what we call transformations. They can be transformed. They can be moved from one position to another. They can be shrinked by changing the scale. But for now, I'm focusing on the standard one or basic one, which is a basic sine graph. So having drawn this graph, what are the observations that we are making? Right. We'll go back. Our domain is x is an element of negative 360 to 360 degrees. And since it starts exactly at 360 and ends exactly at 360, we lock the ends by shading the last point. It shows that we are including both ends. So in terms of interval notation, we use a square bracket. And in terms of the inequality notation, we use a less or equal symbol. Right. So this is your interval notation. That's your interval notation. And then this is your inequality notation. Right. You can either use the first notation as you answer your questions, or the second notation is still correct. Then we go back to range. We did define range earlier on as the vertical distance between the highest point and the lowest point, half that distance. So actually, I mean range, where does the graph exist? It exists between -1 and 1, which are those green lines that I spoke about there. So our graph is trapped between those two. So the y values start from -1 and end at 1. Why are we including both -1 and 1? Is because our graph, if it is supposed to go up, it will touch that 1. And when it goes down, it will touch that line of -1. Therefore, it starts exactly, the moment I say exactly at this is inclusive. Hence, I have used this half inequality symbol and that other half inequality symbol. We call that less or equal a half inequality symbol. Otherwise, it's not a strict inequality symbol. You can't leave your answer as -1 is less than y. These are the y values. Range affects y is less than +1. You can't write an answer like this, because our graph starts exactly at -1 and stops going up exactly at 1. Hence, we don't use a strict inequality symbol. This one is called a strict inequality symbol, because it's strictly greater than -1 and strictly less than 1. Yet, our graph does touch those points. So, we use a half inequality symbol, which is accommodative of those 2 points. It's either it's greater or equals to -1, but less or equals to +1. That is our range. That's how you interpret range. Then we come to the period of the graph. Allow me to take it from the left-hand side. You will realize that our graph started at -360. It goes up, it turns, it comes down, further down, then seemingly it stops. Let me choose another color for you. Seemingly, this wave stops somewhere here. How do I know it has completed its cycle? Because it starts going up again, like this, down, down, further up, then it stops. It's another complete wave. And remember, these graphs start from -infinity up to +infinity. They don't stop, but we can't investigate them from -infinity to infinity, because we'll never get there. So on that note, we'll always choose a domain to observe the behavior of this graph within a specified domain. If behavior is consistent, what does that mean? It means whatever pattern it displays within the observed domain, it will be the same pattern throughout. So our graph starts from negative 360, it goes up, down, further down, then it stops at 360 coming from the left-hand side. That's how we must always interpret them. You interpret them from the left-hand side. Then it starts at 0 going up again. It's like it's the same wave that is now repeating itself. Then the question is, after how many degrees does this work? You'll realize that from 0 to 360, many a times we prefer to use the positive side. So from 0 up to where it comes back to cross going up again is after 360 degrees. From 0 to 360 degrees is a complete wave. That's what we mean by a complete cycle. That's a complete cycle of our basic sine function. Then this will also define what we call the period of the graph, being the number of degrees after which the same cycle will repeat itself. So the period of this particular graph, therefore, is 360 degrees. That's what we mean by the period of the graph. Then how about the amplitude of the graph? The amplitude of the graph is always half the distance from the top value minus the lower value. You want to know the distance between those two values. And in this case, from 1 to -1 is 2 steps going up. Then you divide by 2, you get a 1. So it means the amplitude of this graph is a 1. Meaning, if I go back to the sketch now, if this graph is to displace itself upwards, it can only go a maximum of 1 unit. If it's to displace itself downwards, it can also go a maximum of 1 unit to the lower direction or negative direction. So to either side of the horizontal axis, which is your reference point, that x-axis looks like a reference line. The x-axis becomes your reference line, and these points are placing themselves a same distance maximum on either side of 1 unit away from the line, 1 unit away from the line to either side of the line. That's what we mean by the amplitude of a sine graph. It's how far up it goes from the horizontal axis and how far down it goes from the same horizontal axis, because it's a complete shape that is made up of waves going up and down, oscillating between -1 and 1. Therefore, half that distance from 1 down to -1 is 2 units. If you divide 2 units by 2, you get a 1. So it means the amplitude of the graph is equals to 1. That's how you determine the amplitude of a graph. Even if you were to shift it up, every time you want to find the amplitude of a sine graph, you look at the maximum point it touched, you look at the minimum point it started from, subtract those two to know the actual vertical distance, then halve that distance, find half of it. So basically, these are the properties of our standard sine graph in this specified domain. It says range is -1 to 1. Period is 360 degrees. Amplitude is 1. Then we move on. Okay. My next graph is going to be the cosine graph. It's basically the similar approach. The only difference is that this time around, I am dealing with the cosine function, which on the Cartesian plane you normally define as cosine is adjacent over hypotenuse, which is x over r, as a ratio. But today we are treating them as functions. And maybe I should also have mentioned something here to say, you should also realize why they are functions. Because if you were to draw a vertical line, it will cut this particular graph only once, meaning it's a 1-to-1 function. The sine graph is a 1-to-1 function, hence it qualifies to be a function if I were to use the vertical line test. Okay. Otherwise, if you draw a horizontal line test, remember you are determining what type of a function it is. Is it a many to one? Is it a one to one? And so on. These ones are many to one. Okay. Right. We move on to the cosine graph there. We're basically going to answer the same questions: the domain, the range, the period of the graph, and of course the amplitude. Right. Likewise, we are going to do the same we did with the sine graph. We have our domain. We will space our angles equally the same. And then negative 360 to 360. We go back to our calculator just as a reminder. Step number 1, you press mode. Step number 2, you press table. Step number 3, you enter the function. You enter your function. This time you press cos of x. That x can be theta, it can be alpha, it can be beta, it can be any other variable. But once you introduce that particular variable, know it represents certain angles which will be given to us. In this case, the angles are negative 360 to 360 at a certain spacing. Okay. We follow the same steps as before up until we get to the table. Right, having done that, this table will look like this, the one that you see here. This time around, again, my points are in the form x, y, which we'll need to plot. Negative 360 degrees is your input value. These are the ones that we are substituting into the function to obtain your output value. It goes with a 1, and so on, listing all of them. When I am at 0 degrees, my y value is a 1, and then it will continue and so on. When I am at 360 degrees, the last point, my corresponding y value will be a positive 1. If you look at both ends, they are sharing the same value. It's 1, 1, 0, 0, negative 1, negative 1, 0, 0, then 1. That's the pattern that I'm also picking up. Must get used to this also. Right. Having come up with the table, again, I have to decide what is going to be my y scale. I need to check the minimum value of y. I see the minimum value of y is a negative 1, and the maximum value of y is a positive 1. So my scale must accommodate both negative 1 and 1 on the vertical axis, which are my y values. Then on the horizontal axis, my x values will start from negative 360 degrees and stop at 360 degrees, because this is the domain that I'm given to work with. I can come up with my own domain, but here I'm given x is an element of negative 360 to 360. I think you are observing something compared to grade 10. When you were in grade 10, you never looked at the negative angles. You were only focusing on the positive angles, which is something new that you should be learning today, to say, okay, these graphs, in as much as I know how to draw them from 0 moving forward to 360 and so on, I can as well do the same backwards. I think that's the only new thing that you are observing here, that instead of starting from 0 moving upwards, you can also move backwards with the same steps until you get to whatever minimum value of your domain you are given. Okay. Right, having done that, there is our Cartesian plane. Ignore the graph. It will still come. Pretend it's not there. We're going to mark some points like we did before. Our negative 360 goes with a 1. We mark that point. Our negative 270 goes with 0 if you look at your calculator right now. Our negative 180 goes with a negative 1. Our negative 90 goes with a 0. And then our 0 goes with a 1. Our 90 goes with a 0. You mark those points, all of them. 180 degrees goes with a negative 1. 270 degrees goes with a 0. Otherwise, our 360 degrees is our last point. It goes with a 1. Again, I'm going to join my points to produce a curve, right? So we're going to join our points using a curve, which is this purple curve. We are now seeing that purple curve, and it has to be a smooth curve. And as you draw these graphs, you must just continue moving. Let me quickly show you what I mean by that. Here you are. You have your Cartesian plane like this. You are drawing a graph of some kind. You come down like this. You go up like this. You come like this. You do that. You can see your graph is not well drawn. You don't erase this one. This is your y-axis. This is your x-axis. You don't erase this one. Instead, you can smoothen it out before you rub out what you don't need. You turn smoothly. Then from there, you can so long remove what you don't need. Let me move this to the side. You remove what you don't need, and then you leave the other one. You are smoothening your graph. You're actually smoothening it. You can see here it turned a bit early. You can so long extend and then continue smoothly like that. Then from there, you'll rub out what you don't need. You just move following your points. It may not be perfect to begin with, then smoothen it out, then rub out the things that you don't need. This is exactly how you can draw those graphs. You just continue following your points after point until you get to the end. Then, since it's a closed interval, you lock your ends. You lock your ends. Right, again, what did I notice? I noticed that this graph is also trapped, like the sine graph is trapped between -1 and +1. Already you understand the concept of the range is from -1 to 1. Otherwise, domain, you are focusing on the x values. This graph starts exactly at -360 and stops exactly at 360 degrees. So our domain is going to be x is an element of -360 degrees, just like the sine graph, to +360 degrees using square brackets if you choose that notation. Or you use the other notation, which is in this case, okay, this should be your x, right, which is in this case -360 degrees is less or equals to x, which is less or equals to 360 degrees. Otherwise, your range, we've already seen it, is -1 to 1 inclusively, both ends included. Let's go back to the period again. This graph is also oscillating between -1 and 1. Then the period will again see that it starts at the top, it goes down, then it goes to the top at 1 here. It stops. That's a complete wave. Then the same wave starts from 0 up to 360 and it stops at the top again. That's another wave. Meaning, let me change the color quickly for you. Meaning this graph will move from here and it turns, it stops there, then the other part takes over. You can see in between, these are complete cycles. So from 0 up to the last point is exactly 360 degrees. This graph also has a period of 360 degrees like the sine graph. Same applies to the amplitude. The highest value is 1, the lowest value is a -1. Subtracting those two will give you a 2, half that distance to see by how many units it displaces itself either upwards or downwards. It's a maximum of 1 to either side. So we are realizing some similarities here between the two functions. Both functions share the same domain that was given here, and then both functions have the same range. Both functions have a period of 360 degrees, meaning they complete their cycles, whatever cycle, they will complete it at after 360 degrees. Both functions have an amplitude of 1. That's what I have observed so far as we are doing this together. Right, we're moving on to the next graph. Our next graph is going to be the tangent graph. The question reads, sketch the graph of the function f of x equals to tan x in the interval x is an element of negative 360 degrees, and then determine the domain of the function, determine the range of the function, the period, and as well as the amplitude. Like the other two functions that we have just done, we'll find all those characteristics of these graphs: the domain, the range, the period, and the amplitude. As you define these graphs, like we indicated earlier on, you need to define them in terms of their periods, in terms of their amplitudes, as well as in terms of their domain and range. That's how we define these functions. That's how we interpret them. Right. So in this case, I'm going to focus on the tangent graph over the same domain, negative 360 degrees to 360 degrees. Okay. Right. We are going to come up with a scale here, and for some reasons, I used a particular scale today. My scale, or spacing rather, I'll space out my angles using 45 degrees on the horizontal axis. I'm not sure of the vertical axis yet. I shall see after coming up with my table. Focus on the question. Step number 1, we go back to the same steps. You press mode. Let's do that quickly. Press mode on your calculator. Then you go to your table for function. You enter your tan x, just like before. Then enter, it will say start. You enter negative 360 degrees. Enter, it will say end. You end at 360 degrees. If it requires step, you'll put your step. In this case, our step is going to be 45 degrees. I will explain all this later, how I chose that 45 degrees. I can't use 90 degrees today. There is a reason. Right, step 45 degrees, then enter. Yes, you'll get a table like the one that you see on my screen there. At negative 360 is 0. At negative 315 degrees is a 1. At negative 270 degrees, there is no number. Some calculators will put some broken lines. Other calculators will say error. What does that mean? It means we can't define, because we want an output value here when the angle is negative 270 degrees. And apparently, there is no such a value that exists at that time. Therefore, it means at that point, the graph does not exist, because we can't get a number that will match or make a complete ordered pair. Then it continues to negative 90 degrees again. You'll still find the error there on your table. That error indicates that we can't get a value. Even if you just press directly on the calculator, tan of negative 90 degrees, it will say error. What does that imply? It means there is no value that goes with that particular angle. So you'll find that on this tangent graph, there are specific points where there is no corresponding y value. So we want to have a look at how we interpret that graphically. We are going to plot these points, point after point. But we are going to have a problem today, because somewhere along the way, there are points that we can't plot because they are incomplete. Not incomplete because we failed to find the value. Incomplete because there is no y value at that time. Okay. Then looking at my scale now, I can see it starts from -1 to 1, so I can as well design it that way, going up depending on the nature of the graph. Right. If I were to plot these points now, you are going to realize the following. There are these red broken lines that I've shown there, where the y values were not defined. It means these are called lines of asymptotes. This is what we mean by a line of asymptote. It means our graph won't cross that line. Whatever graph is coming, it won't cross that line. Minus 270 is one of the vertical lines that the graph won't cross. It's an x value. In other words, that is x equals to 270 degrees. At x equals to negative 270 degrees, our graph won't cross that line because there is no corresponding value of y. And again, when x equals to negative 90 degrees, our graph won't cross. Then we realize there is a pattern here. After every certain number of degrees, which in this case I see is about 180 degrees, the same line comes again. X is equals to positive 90 degrees now. It's another line of asymptote. There is no corresponding y value. And so on until we get to x equals to 270 degrees in this domain. There are those 4 points where the y values don't exist. These are called lines of asymptotes. The graph won't cross those lines of asymptotes. So when we start plotting our points now, we realize that at negative 360 is a 0 there. Then as we go closer and closer to 270, you can pick any other angle, maybe negative 350, negative 300. You'll find that the values are positive up there, getting closer and closer towards that vertical line. Then we'll draw a curve moving closer and closer towards that vertical broken line. In other words, our graph won't cross that vertical line. It gets closer and closer but won't touch it because there is no corresponding y value. Hence, it's bounded. That is a boundary. It can't cross, neither can it touch because there is no specific y value at that time. Then in between again, when you pick a value which is negative 260 somewhere here, the y value is a negative value down there. When you go to 180, it's a 0 there. When you go to negative 170 somewhere there, or 150 is somewhere up there. We find that it's a wave that moves vertically upwards and downwards, upwards and downwards, and is trapped between the broken lines. That wave can't cross either broken line. This is what we mean by lines of asymptotes. So these graphs will cross the x-axis, moving closer to a line of asymptote, which is a line that the graph approaches but will never touch. So this one we can see is trapped between two, towards the positive side of y is getting closer and closer, towards the negative side of y is getting closer and closer to the other asymptote that we have just passed. Therefore, at any given time, this wave will always repeat itself, same shape throughout, but is always trapped between what we call lines of asymptotes, which are those lines that failed us as we were trying to find the corresponding values of x. So those are defined as lines of asymptotes. Our graph will always get closer and closer to those lines, but will never cross them. So the tangent graph also has its own period. Its period appears in two forms. You'll realize that there are lines of asymptotes. They will appear after a certain number of degrees. The same applies to this black wave. It will maintain the same shape throughout and will appear all the time trapped between two lines of asymptotes. So the tangent graph does not oscillate like the sine and cosine moving up and down. It goes up to infinity, upwards, and down to minus infinity forever. It's not bounded going down. So for the y values, it will continue going to negative infinity, then continue going to positive infinity, meaning it will forever be moving upwards and forever be moving downwards, but is trapped between two lines that are vertical and broken. Those lines that are vertical and broken are called lines of asymptotes. This is how we draw the tangent graph. And of course, we have to lock our ends like in all other graphs. If it's a closed domain, you lock the ends. That's our tangent graph. Then, what is this domain? It was given as negative 360 to 360. Then the range now, if we go back to what I've just mentioned, this graph does not start at a particular position. It continues moving downwards to negative infinity. It will continue moving upwards to positive infinity. As you get closer and closer towards a line of asymptote, the y values will get bigger and bigger going up, smaller and smaller going down, and will never stop moving. Hence, the range of the tangent graph is negative infinity to infinity. There's an error here, we remove this. It's from negative infinity to infinity. In other words, y is an element of all real numbers. It's an element of all real numbers, which is from negative infinity to infinity. That's where that graph exists. Going down the y side. Then going the x side, we're given a closed interval. Right? Must take note of that. Every time you are using infinity, you don't put a or equal or a half inequality symbol because you never get there. Some learners can choose to write it as y is an element of, you use this notation from minus infinity to infinity is allowed. But you must use a curving bracket this time around to avoid accommodating both negative infinity and positive infinity. You'll never get to these. So this is out. Must not consider that. Right. Then we go back to the period. After how many degrees do we see the graph appearing? So the graph crosses at 0 there. It crosses again. It appears again at 180 degrees. It appears again at 360 degrees. As you start it moving forward, you will find that after every 180 degrees, this graph will always appear, but trapped between some particular lines of asymptotes. Hence, the period is 180 degrees. Then, how about the amplitude? Are you going to say positive infinity minus negative infinity divide by 2? Well, you can do that, but it's not recommended because you'll never get to infinity. All we can say is that the amplitude of a tangent graph does not exist. In other words, is undefined because you can't define infinity. So the answer to the amplitude of a tangent graph is undefined because it's unbounded. It's endless to either side on the y. Hence, we say it is undefined. So as we compare this tangent graph to the cosine and sine graph, you will find that this one does not oscillate. It's a wave that moves towards the positive infinity of y and towards negative infinity of y. Right? Secondly, its period is half a revolution, which is 180 degrees. Otherwise, its amplitude is undefined. So here are my 3 graphs now put together. The same graphs that we're dealing with. The blue graph is our sine graph. The orange graph is our cosine graph. They keep on intersecting, crossing each other here and there. You can even find distances between the graphs at some points. For example, here you can know when was the distance 1 or half between the values. This one is a distance of 1 unit if you were to compare them. You can be asked any question based on all these graphs drawn on the same Cartesian plane. So you need to know how to interpret it. But for today, I'm not going to interpret any graph. I'll just draw them like we have just drawn them and compare them on a Cartesian plane. You can see when x is 0, the cosine graph is at 1, but when x is 0, the sine graph is 1. Otherwise, the tangent graph is also 0 at that time. So at the end of the day, these are the waves that we are going to see for the cosine graph, green graph, and the sine graph, blue, and then the cosine, orange. when they are drawn on the same Cartesian plane from negative 360 to 360 degrees. And they are all logged at the ends. There are some lines of asymptotes along the way for the tangent graph. Otherwise, cosine and sine do not have lines of asymptotes. Right, so what are we saying? We are saying if we were to look at all those three graphs, summarizing them in a tabular form, this is what we mean by the three basic trig graphs, standard ones, sine, cosine, and tangent. For the period of both sine and cosine is 360, but for the tan is 180. Then for the range, for the y is negative 1 to 1, negative 1 to 1, that is both x, sine x and cos x. Otherwise, with the tangent graph, is negative infinity to infinity. Let's correct that bracket. Then the amplitude is 1 for the sine graph, is also 1 for the cosine graph. Otherwise, is undefined for the tangent graph. Then how about lines of asymptotes? So far, there is only one graph that has lines of asymptotes in our selected domain. It was the tangent graph that has lines of asymptotes at plus or minus 90 and plus or minus 270 degrees. That's what we observed upon sketching them. Then interval spacing, I'll talk about this just now. Interval spacing for both sine and cosine, we use 90 degrees. Otherwise, for tangent, we use 45 degrees. This is standard. That's why I chose 90 for sine and cosine and 45 degrees for our tangent. How do we define the spacing when you draw or sketch these graphs? There is a formula that we use. The interval spacing, I didn't want to show you the formula earlier on because it speaks to the period of the graph. And at that time, we didn't know what is the period of our graph. Now that we know the period is 360 for both sine and cosine, if you divide the period by 4, it's a formula that we use, and it was proven that it makes the diagrams come out neatly. Meaning you can use any other number less than 90, but the maximum that you can use is only 90 degrees. So it was discovered that when you take the period and divide by 4, the graph comes out perfectly well. You can use any other number as long as it is less than 90 degrees. The graph will always come. Otherwise, if you just pick any other angle to space out, you might find that some points will, actually all points will lie on the horizontal axis and produce a straight line that is horizontal. So to avoid that problem, there is a method that we use to come up with a spacing. We take the period of the graph, we divide by by 4. So for sine and cosine, we say a spacing is equals to period, which is 360 degrees, divide by 4, it will come to 90 degrees. That's how we are going to space them out. That is for sine and cosine. Then for tangent, now that you know the period, so our spacing for tangent is going to be the period, which is 180 degrees. You divide this by 4. It's a standard formula. It gives us 45 degrees, and hence we spaced out our angles using 45 degrees. Right. So here are the important things to notice about these graphs. I've already mentioned that both graphs of sine and cosine have a period of 360 degrees. And then both graphs intersect the intervals after every 180 degrees. If you check, then both graphs have an interval spacing of 90. Otherwise, both graphs have an amplitude of 1. Those are the most important things on these two functions. Then for the tangent graph, we'll always have a period of 180 degrees, and the lines of asymptotes will also space themselves out after every 180 degrees. Same applies to the curve itself. It will space itself out after every 180 degrees. Right, we proceed. This time around, I want to have a look at the effects of the parameter k. The parameter k on the functions f of x equals sine kx, and f of x equals cos kx, and f of x equals to tan kx. Right, it should be observed here that this k I have introduced is a numerical value. It's a number. In other words, I can say y is equals to sine of 2x. What happens if I introduce a 2 there? In other words, this 2 that I've introduced is what we mean by a parameter. We have introduced, in other words, we are doubling our angles. You can even use a half there, it will also work. You can use any number there as long as it is a positive value. Your k has to be a positive value. Even if you use a negative, in any case, you'll have to reduce that. But for now, we focus on positive values for k. Sine half of x, sine 3x, sine a third of x, sine 5x, and so on. That's what we mean by a parameter being a value that you introduce to the angle or to the function to change it, to transform it from being a basic graph, standard graph, to a transformed graph. These are transformations. They affect the graphs in a particular manner. So I want to have a look and see what happens if I introduce a 2 to the angle and have sine 2x, which is now doubled, in the same interval or choosing another interval from negative 180 degrees to 360 degrees. We'll again determine the domain, the range, and the amplitude, as well as the period of those graphs. Again, we are going to use our table method, which is what we are quite familiar with now. But before I use the table method, I need to decide how do I space out my angles. That is very, very important. I've decided to space out my angles this time using 45 degrees. I'm not going to explain for now how I got that 45. Only at the end, you'll see why is 45 degrees. I will give you that information. Is 45 degrees spacing out, but later on you'll pick it up why is 45. Again, we are going to come up with a table like you see on the board or on our screen. We have our table here. It's completed the same way we have been completing other tables, but of importance this time, we are going to say mode, table. When you get to the function, what do? You press sign. Let's do that. Mode, table, then you press sign. Stop there. Remember, this time around, we are drawing the graph y is equals to sine of 2x. You'll have to feed the 2 first, then alpha x. On the screen, you will see sine 2x. Then you proceed. Then when it says step, we are going to use a step of 45 degrees. I want you to use a step of 45 degrees. Then you enter and continue and obtain the same table that you see on my screen. Your beginning is negative 180 this time. Your end point is 360 degrees. Having done that, there is my scale from negative 1 to 1. Seemingly, these values start from negative 1 for the y side and stop at 1. Same as the previous graph of sine, the original one, the mother one. Some people call it the mother graph or standard or basic. Already I can see the amplitude here. I can also see the range. Then you are going to again plot point after point. Negative 180 is 0, negative 135 is 1, negative 90 is 0, negative 45 is negative 1. You plot all your points right up to the end, point after point until you get to 360 degrees. Then you lock the ends. You already have an idea of the cosine graph, that it is a wave that oscillates between some values. Right. So again, this one oscillates between negative 1 and 1. It's taking the same shape, but seemingly something has changed here. I remember the original was 91, but this time is 45, 1. That's what I'm observing here. 90 degrees is no longer 1, it's now 0. Because we are doubling those angles. What was a 90 now becomes 180. What is a 45 now becomes 90. And we know sine 90 we saw is a 1. So that's why 45 degrees now goes with a 1. There is our 45 going with a 1. That's what we are observing there. Right. Then, what are we saying? We are realizing here that as we continue moving, and if I focus on the, let me see the color of my, yes, starting from 0, this red wave ends at 180. From the 180, a blue wave takes over, same as the red, up to 360 degrees. From A to B is a complete wave. From B to C is another complete wave. Within a revolution of 360 degrees, I now see 2 graphs that are complete. I now see 2 cycles that are complete within a revolution. Maybe that's the effect of that too. Because I remember on the original it was just 1 complete wave in a revolution. This time I'm now seeing this red part A to B, B to C. Those are complete cycles on their own. What does this mean? It means there are now 2 complete sine graphs within a revolution by introducing that 2. So what does that imply to me? This graph has 2 complete sine waves within a revolution. Hence, the frequency of the graph is 2. That 2 I introduced speaks to the frequency of the graph, meaning from 0 to 360 degrees, how many times will I see a complete sine wave? I will see it twice. Oh, in short, I'm dividing that period of 360 into 2. Because this graph now completes within a short space of time, which is after 180 degrees. Okay, the first complete wave is from point A to point B, and the second complete wave is from point B to point C. Each wave has a period of 180 degrees. It's no longer 360 degrees. So meaning that too has an effect. Therefore, it means the new period of the graph, f of x equals to sine of 2x is now 180 degrees, is going to be given by period divided by k. You go back to the standard period, you divide by k. Our standard period is 360 degrees, divide by 2, it comes down to 180 degrees. So when I introduce a 2 to x, it means I'm going to have a frequency of 2 in a revolution. I'll see 2 complete cycles, and then the period is no longer 360, it's now 180, 180. Oh, so this is the effect of multiplying that variable x by 2. It means I will see 2 complete sine graphs in a revolution. Then the period has come down to 180, which is basically period of the standard graph divided by 2. Therefore, again in conclusion, I see my domain is negative 180 to 360. My range is negative 1 to 1. Otherwise, my period of the graph is going to be the standard period divided by 2. Because there are now 2 complete cycles within a revolution, they will have to share the standard period of 360 degrees. So each complete wave will have to take 180, then the other wave will take the next 180 to make it a complete cycle of the standard graph. The amplitude still remains at 1. So the effect of adding a k, parameter k, or number k to the variable of the, which is the angle, is what we are just seeing here. That k will speak to the frequency of the graph to say how many times do I expect to see this graph in a revolution. If it's a 2, I'll expect to see it twice. If it's a 3, I'll expect to see it 3 times. In our original, it's a 1. That's why we see it once in a revolution. Then how is the period affected? You divide the standard period by that same variable, k you introduced. It will come down to the new period of your graph. Then we come to the cosine graph. Likewise, we are going to come up with a table, same as before, but this time is cosine. Our function is f of x is equals to cos of 2x. I've decided to introduce a 2 again here. Then I'll follow the same steps. Punch on the calculator. The step, they said I must maintain that 45. Maybe I must go back and quickly explain why you use the 45 there. Your new period for your spacing, how I got my 45. For my spacing, I took the new period, which is 180 degrees for the new graph. You divide by 4, then it will give you that 45 degrees. That's why I spaced out using 45. Then for the cosine graph, again, I'll use the 45 degrees for some reasons. Then I'll come up with this new table now, from negative 180 to 360 degrees. I've decided to introduce a parameter. This is my graph f, which is defined by y equals to cos of 2x. Plotting the points again, negative 180 is 1, negative 135 is 0, 90 is negative 1. You mark all your points. That's what we mean by point after point. Point after point. You can see they are moving up and down, but they seem to be stopping somewhere. That's your cut-off maximum. This is your cut-off minimum. Again, this graph is still trapped like the standard cosine graph. But what I'm noticing here again is that the range is still the same. Your domain is negative 180 to 360 degrees. What I'm noticing again here is that if I start at the top there, I go down with my graph, I bend with it, I stop there. It's like it's a full cycle because it starts going down again, that purple graph. Okay, right, there we go. Our graph starts here, looking at the positive side, and it stops at B there. So we are saying the graph has 2 complete cosine waves again, like the sine graph within a revolution. The first cycle starts from A to B. The second cycle starts from B to C. Again, we notice that there are 2 complete cycles within a revolution. Hence, the frequency is 2. That's our frequency. When we say frequency, we are saying how many times do we see the same complete cycle showing up. It will show up twice. Frequency is 2. Then the period, each frequency of the cycle has a period of 180 degrees. It has come down from 360 to 180 for the same reasons that we mentioned in the sine graph, where we introduced a parameter k, where our k was a 2. So this parameter k we introduced in this case, our k is a 2. Our k can be a 3. Our k can be a half. Our k can be any number. So if you introduce a parameter k, these are some of the effects on these particular graphs. They tend to move faster and complete their cycles within a short space of time. This one has completed this cycle within 180 degrees. That is its new period. Okay, same as the cosine, as the sine, there is our range still negative 1 to 1. It's not affected. Then our period is affected. It comes down to 180. Otherwise, our frequency is 2. Then the amplitude still stays at 1. And so far, what I've observed is that when I introduce a k, what's affected so far is the period and the frequency of the graph, to say how many times do I expect to see that particular graph. Okay. Then likewise with the tangent graph, we have sketched the graph of f of x equals to 2 tan 2x. I've introduced my parameter k is a 2, but this time I've chosen an interval of negative 180 degrees to 180. Then my spacing, this time I'll use 22.5 degrees for some reasons. Then we'll have a look at how the graph will behave. That's the tangent one. Again, we are going to fit, this is your f of x is equals to tan of 2x. We have introduced our parameter k is 2x. That's the k parameter. Again, I see some lines of asymptotes, but I've changed the step. It's now 22.5. If you sketch this graph also, this is how it's going to behave this time. My lines of asymptotes are now at negative 45 and at positive 45 and so on. I can also determine after how many degrees do these lines of asymptotes appear. I can see it's at negative 45, 45 is a gap of 90. The next one I will add 90, it will be at 135 degrees, it will be another line of asymptote. And so on until you get to 180 degrees. And so on until you get to negative 180 or negative 360, depending on what you are given. This is the behavior of that graph now. What I'm seeing is that my lines of asymptotes have shifted. Initially it was at 90, it's now at 45 because of that parameter k I have introduced. What was my line of asymptote as 90 degrees is now 45 degrees. And I can see these are now having a span of 90 degrees. It's no longer 180 degrees. Then the period of this graph, you can see it starts from negative 90 here. It continues again here at 0 and so on. If you start this, is after every 90 degrees. The way the branches are now spaced out, meaning the period of this new graph is now 90 degrees. Even if I were to add other angles until 180, you will find that it will maintain the same period of 90 degrees. Meaning again, our period is going to be the standard period, which is 180 degrees for tan. You divide by 2, it will come down to 90 degrees. This is going to be your new period. Otherwise, your spacing is now going to be 90 degrees, which is the new period, divided by 4, it will come to 22.5 degrees. That's how I'm going to space out my angles to come up with my new graph. Again, we realize that within this 180, we are going to, actually within 90 now, we are going to have 2 branches. And then secondly, our period is going to be affected. It will come down by another 90, which is 180 divided by 2. So the new period of this tangent graph becomes 90. So basically, the effect of k to a particular function affects the number of times you will see that graph for sine and cosine within a revolution. Otherwise, with the tangent, it will define new lines of asymptotes. It will also define a new period, which is now 90 degrees, 180 divided by 2. And your spacing will now further come down to 22.5. Okay, so our range is negative infinity to infinity. Still need to correct this, it came earlier on as an error. Right. Then the period of the tangent graph is the basic period, which is 180 degrees. Divide by 2, you get 90. The amplitude is still undefined. Again, the period is affected. The frequency is also affected. Okay. Right. In conclusion, we're still having the same as before. For these 3 functions, our period for both sine and cosine is 180. Otherwise, for tan is 90 degrees. The range is still the same for all the three. The amplitude is still the same. For this other one, it's still undefined. Asymptotes, they still don't have asymptotes. But for this one, our lines of asymptotes will change from plus or minus 90 degrees to plus or minus 45 dividing by 2, plus or minus 270 degrees divided by 2, plus or minus 135 degrees. I guess you can see the effect of that 2, which was okay. You divide the points of asymptotes again by 2 to define the new asymptotes. Otherwise, our spacing, this one is now 45 and 45. Then for the tangent, it's now 22.5. Bearing in mind that spacing is the period of the new graph divided by 4. So we're now focusing on 180, 180, and 90. Divide all three by 4. You will get the corresponding spacing angles. Right. In general, for the functions f of x equals sine kx and f of x equals cos of kx, both the graphs will have a period of 360 degrees divided by k, because one wave covers a pattern of 360 degrees divided by k. The same applies with the tangent kx. The period of the graph is going to be 180 degrees standard divided by our k. Otherwise, our lesson is going to end here, but before I close, I've left you a worksheet that you need to go through. You need to sketch the graph of given functions. F of x equals to sine 3x and g of x equals cos half of x in the given interval by first completing those tables. We have g of x and f of x is a 2-in-1 type of a table. For 8 marks completing the table, just to practice that. Then from there you sketch the graph or the two graphs. After that, you answer these questions. Use the sketch of to answer the following questions. X element of negative 180 to 180, you need to determine the range of the graph, the range of G, range of F, period of G, period of F, the amplitude of the graph F. Then determine the values of X for which f of x is equal to g of x. Where are they equal? Determine the values of x for which g of x minus f of x is equal to a 1. You need to check that region where the two graphs have a gap of 1 when you observe or study them. Otherwise, this is your worksheet. And in conclusion, I'm going to summarize. What did we look at in this exercise or in this lesson? We were looking at the sketching of a graph of any trigonometric function defined by y is equal to sine x, y is equal to cos x, and y is equal to tan x for the given domain x element of or theta element of negative 360 degrees to 360 degrees by using what we call point after point or point by point plotting. We also looked at the description of a function in terms of its amplitude, period, and frequency. We also investigated the effect of the parameter k, but in particular and of interest is that the periods get affected by that k. You take the standard period, you divide by k, then you'll get the new period. Then the k itself will tell you about the frequency of your graph, how many times the graph appears. Otherwise, we are going to stop here for today, and thank you for attending.